So for instance, when dealing with the problems of classification of data and supervised learning, right, we have shown how one can use, right, residual neural networks, right, in a given dimension D in order to, layer by layer, right, make information evolve, right, and succeed on, in particular, classifying in a successful manner so that eventually this can be later used for generalization, right, to classify new data that are unknown. So as we have seen, basically, the way we, the perspective we adopted was that of nonlinear dynamical systems, either continuous in time or discrete in time, governed by a sigmoid nonlinearity, right? And manipulated, regulated through parameters, controls depending on time, that were taking into consideration the possible need of, shifting the interface of the neural network in the Euclidean space, so to better classify, orienting also to choose the cutting hyperplanes that will determine what is the move region and what is the one that is frozen, and then also orienting the wind along which the moving region will move, right? And this was done in dimension D, right, with a given, say, width for the network. But you see, in view of this idea, you see that this idea can be easily extrapolated also to the context of neural networks. Of course, this is a very general idea. Details have to be worked out later, right? So the analysis might even be complicated. So the analysis of the perfectly matching layers that was actually introduced for the Maxwell's equations in elasticity, where this is actually a system of wave equations, is not simple. The idea is quite generic. As we said, given any system inside this box, any process, any continuous media evolving inside this green box, we can always set up a little, say, layer around. And in this layer, the equation can be tuned arbitrarily because after all, right, once we solve the equation in the big domain, we are, neglecting everything that has been added here artificially and focus simply on the equation and the solution inside the original domain. So then even if originally, we have added this artificial term, because this artificial term is only active on the exterior layer, we can focus, right, and restrict the solutions to the original domain so that we preserve the true equation. So, as I said, then the analysis needs to be, justified. But computationally, this is something that is actually extremely useful and not so hard to implement. And one can, of course, soon realize, impact that such a damping mechanism has on the behavior of solutions. So this idea could be also implemented in the context of deep neural networks. So how you will do it? I mean, you have to, right? If I will ask you, okay, can you extrapolate this idea that originates on the wave equation, on wave-like equations, by adding exterior layer of damping material? Could you generalize it to the context of, neural networks in which we are, moving from one, say, layer to another, right? To another, so to generate a map, right? That out of a That was our original problem, right? Out of a cloud of very mixed data, right? Is able to really, place the data corresponding to each label well separated in the arrival space. How will you extend this idea to that setting? Note that the phenomena could be similar here when we are advancing, we are marching on K, which is the pseudo time on our deep neural network, or the real time in case we decide to make it an ordinary differential equation to work with neural differential equations, right? So, but the phenomena could be similar. So, for instance, here, we know that the wave equation, right, is oscillating inside, but when getting to an artificial wall, waves will bounce back, generating, phenomena that are spurious. This is why we decided to continue, right, the wave equation outside, let waves get into the added frame, but add the damping there so that they never come back, right? Of course, this idea can also be implemented in the context of neural network, right? You could always say, okay, no problem. I add one extra layer here and one extra layer here, right? I make the network a bit wider. I design the coefficients for the wide neural network, but then eventually I try to project into, the original width, right? And in this way, the fact that I am allowed to add an extra layer up and down, right? This will allow me, for instance, to introduce dissipative effects here that will have an impact also in the original network. And this might, for instance, allow to improve the stability properties of the network, which of course are very important for generalization, right? Because somehow our comprehension of these topics is that, even though you train a network with a given data, even though you might succeed very well with the data you have, right? If the neural network, which is actually a Poincare map, right, from input to output, if this nonlinear map is extremely oscillatory, right, this can be a bad idea for generalization, because small variations can lead to very, large, distances at the arrival. So it might be also a good idea that in the context of neural networks, we implement this kind of tools, meaning increase the width, use the added layers to maybe damp, right, the system, so to try to assure further stability properties of the neural network. Okay. So I'm not saying, I don't even know whether anyone has done this. As you know, there is a huge literature on machine learning and neural networks. Oftentimes the terminology is completely different, right? I suppose that if you look for a paper under the title perfectly matching layers for neural networks, maybe there is nothing. You could try, right? Let me know in case you find something. But it could work that this idea, which is physically extremely natural, has been to some extent already explored. Otherwise, this will be a very nice thing to consider. We could say the same about heterogeneous media, right? So as we have seen yesterday, and this is something that is very important in the theory of and for new materials, for composite materials, material sciences, we have seen that when we are in the context of partial differential equations, right, the mixing of two materials can lead to phenomena which of course are related to averaging. So it's clear that if you merge two materials through a microstructure, you will get a hybrid material that is completely intuitive. what is not so intuitive is what is the property, right, of the materials you are getting, right? So this is more tricky, right? So in particular, as we have seen yesterday, right, when you mix a material with diffusivity coefficient 1 or elasticity coefficient 1 and 2, respectively, to a 50%, you don't get a material with diffusivity or elasticity coefficient 3/2, as we will have expected. But we actually got, I think it was 4/3, right? We got 4/3 here, 4/3. And the reason for this 4/3 is that actually when you are, so the reason is that when you are combining, right, two systems, right, now you try to combine, right, so we try to combine these two, the way the solution responds, right, depends very much on how the solutions X and Y are, you know, responding in each of the cases, right? And of course, the solution X on one is A minus 1B, and the solution in the other is A2 minus 1B, meaning that when you do the averaging of the matrices A1 and A2, you do some kind of combination of these matrices, right? The solution is rather behaving as an average of, you know, the resolvent A minus 1 and the resolvent A2 minus 1, right? And this is what we have seen here, right? So in the context of homogenization, it was a very simple limiting process in which we make this microstructure finer and finer and finer and finer so that we get an homogeneous color out of the mixing of two different colors, right? And then what we have seen is that in order to pass to the limit and clearly understand how the solution of this mixing procedure will look eventually, right? We don't do it on the model, we don't do it on the PDE, but we do it on the solutions of the PDE, which is actually our quantity of interest, right? So I would like to understand how this, you know, heterogeneous elastic medium is responding to the forces, right? And in order to analyze that, which is, this is the U epsilon, right? In order to understand this, what I do is, okay, let me look to at least to try to guess what is the limit of U epsilon X, right? So we try to understand what is the limiting behavior of the solutions. And this is precisely what we discovered, that because when you try to solve the equation, you have to divide by sigma, leads to the averaging of 1/sigma. In particular, it leads to the geometric averaging, right, of the two coefficients. Of course, in the context of homogenization, you do another example. You could say, okay, what happens then if sigma x is equal to, say, 1 in 0, 1, and then sigma is, say, 2. This time is not 2 in the interval 0, 1, 2, but it's in the interval 1, 3, right? You say, oh, then sigma is periodic, is 3 periodic, right? So we have a sigma given in the interval, right? 0, 3, taking value 1 in the first interval, and then the value 2 in the interval, which is twice longer, right? This is 0, 1, 2, 3, right? So now you see clearly that I am using the value 2, you know, 66% of the time, and then the value 1 only 33% of the time, with a fraction, volume fraction equal 1/3. And then I know that, of course, the relevant homogenized coefficient will be the inverse, right, of the average of 1/sigma, and the average of 1/sigma is the integral from 0 to 3 of 1/sigma, right, dx, and this is, of course, 1/3 And then the integral from 0 to 3 becomes 1, because during the time or the space interval 0, 1 of length 1, I have the value 1. And then I have also, right, another coefficient, which is here 2 times sigma was 2. So it will be 1/2 times an interval of length 2. So I have 1. And therefore I get 2/3, right? So you see that actually the coefficient sigma, so is it correct? So I take in the interval, I do the averaging, 1/3, integral from 0 to 3 of 1/sigma, which is 1 plus 1/sigma, right? So, okay, so you see, this is what we get, right? Sorry, it's the inverse of this, right? So is the inverse, is the inverse of the averages. So in the inverse of the averages, so you get now 3/2. Of course, the solution has to be always, you know, when you mix coefficients 1 and 2, you expect the response to be something between 1 and 2, and this is what you get, right? So you see, it's not totally intuitive in the sense that in order to get a material which has the material properties, which is just the, you know, the average between 1 and 2, you don't do a 50% mixing, right? But here you take rather, say, right, you take a volume fraction here 2/3, while here on the red you are taking the volume fraction 1/3, right? So this is to say that, well, when you are moving into, you know, continuum mechanics models or even say dynamical systems in which there is some kind of oscillatory pattern, right? You have to be careful about what the behavior of the solution will be, right? You have also, you know, for instance, the Floquet theory for ordinary differential equations with periodic coefficients, right? It talks precisely about this, right? So how do the solutions of periodic ODE behave, right, depending on the initial datum you take, right? And as you know, there can be resonances and or quasi-periodic solutions. The behavior is quite subtle, and this is precisely what the Floquet theory tells you. So what is the conclusion we draw from the perspective of neural networks? Well, it's very much the same as I said before. In that case, we are in principle on a different context, right? Our objectives are in principle completely different. It's not about solving a mechanical system for a string equation or, you know, or computing the trajectory of some satellite on a, right, on a periodic system. It's about data manipulation, and we are free, right, to generate the neural network the way we like. But what we have understood, right, in this context of continuum mechanics is that, you know, the periodicity and oscillations, right, both matter, right? And you can, you know, put this periodicity and these oscillations, right, both, right, on the time variable, which is the horizontal variable here, the pseudo time variable on the deep network, or also, if you want, you can also put here, right, periodicity and oscillations, right, along the width of the network. This will be, you know, here, putting periodicity here will be the analog of adding the periodicity with respect to X, as we did here, right, in the context of homogenization of materials. And the Floquet theory, right, will be the analog to, put in the periodicity on the time variable. So actually, in order to understand better what I'm saying about the Fouquet theory, going back to the wave equation, let us analyze something that is extremely, it's not very difficult, but the first time you see it, you say, oh, it looks like odd, right? It looks strange. And it's important because it precisely indicates to you that when you really, rather than, moving on dynamic systems that are constant in time, you do it on periodic patterns, right? It is not so easy to guess what's going on, right? So let me then consider here the wave equations with time-dependent coefficients, right? And I insist that even though in principle this is meant to, analyze, right? This kind of model, right? This is also a warning, right? When you are, say, considering neural ordinary differential equations, right? Because here, right, the coefficients of the deep neural network depend precisely on time, right? And very often, our intuition is very much, conditioned by, a very simple way of thinking, short time, coefficients that are nearly constant. And it's for us quite difficult to figure out what, for instance, a periodic pattern, right, on the coefficients of the system under consideration could be, right? And precisely, let me remind you that actually, the comment I made here, right? The result I presented on the universal approximation theorem and the simultaneous control of neural differential equation indicated that, well, it's quite surprising, right? Because a neural differential equation in which the coefficients are tuned piecewise constantly, right? We were just, defining motions on the plane horizontally, vertically, up and down, and then switching from one to another. We succeeded, like in the Rubik cube, we succeeded to move from a, configuration of complete disorder into a new configuration where you have a complete satisfactory classification, right? So then you see, okay, it seems indeed that it's important to understand, right, how time evolution can play a role on, also, neural differential equations. But before doing that, let us do it maybe in the context of a system that we know better, right? The wave equation. So what did we learn about the wave equation? We learned that when, rho t is equal to rho is a constant, right? Independent of t. For instance, rho equal 1 to fixed ideas. If I take this wave equation, right? We have seen that the energy, which is half of the integral over omega of gradient y squared plus yt squared, is decays exponentially, okay? And this is a very important stabilization result, right? So this is something also that you can expect, for instance, for the systems you are considering in the context of machine learning, right? You expect that at a given time, the systems stabilize, right? And this is precisely when the system stabilizes that you can stop the process, right? So for instance, if you are considering a process for, generating, creating, building new composite materials, right? What you will do is you start, putting material A, material B, material A, material B in a very, strategic manner. So to try to mix the way we said with a given, say, volume fraction of one or the other, right? But then what you expect is that this process will stabilize in the sense that the mixing will be more and more efficient and eventually will reach to a level in which you could, you could cut the process, stop the process, being sure that the new material you have achieved will have the quality and the properties you need up to a, 0.0001%, okay? So this is why the stabilization properties are so important, right? This is, the fact that the energy goes to zero is just a very simplistic manifestation of something that normally, you look into a different context. Wherever the goal is, right, you will really like to make sure that your process is converging to that goal as fast as possible. And of course, even though this is an asymptotic result, right? In mathematics, you will need to wait until t equal infinity to see that really the energy is going down exponentially. In practical applications, you make use of this, right? You make use of this idea on a finite time window, right? Because you simply enjoy a property that the decay, right, is fast enough so to guarantee that this is smaller than epsilon when the time capital T is sufficiently large. And you recall the proof of the result was very simple. It was, move from the energy into a different energy, the epsilon, and then use the fact that, the energy of the system is spontaneously dissipated by the damping term, right? And then the other piece we added to the energy, right? Inspired on these ideas of Lie brackets, Kalman brackets, and hypocoercivity and hypoellipticity, it was meant, right, to, extract out of this dissipation law, right, which apparently simply says that we are dissipating the kinetic energy, make it also explicit the dissipative effect that this damping mechanism has on the potential energy of the system, okay? Very good. But now what happens if I take, as I said, I take a wave equation with time-dependent coefficients? So what is the energy to begin with? What is the energy here? I could say, well, so this is what? This is the wave equation for a membrane for a string. Here I have a coefficient rho. According to, the modeling mechanics, this is a membrane or a beam with density. This is the density coefficient rho, which is depending on time. And I have a damping term. Okay, but if the density depends on time, so maybe what I should really do, right, is just to consider, right, the corresponding energy in which, I multiply, of course, the kinetic energy by rho, while the potential energy, right, is independent of rho, right? After all, right, the rho term only affects the acceleration. That's indeed very natural. So let me now compute the time derivative of the solution of the energy. What do I get? I get that the time derivative of E, right, now is going to be, right, I see already in the first term, I will get two terms, right? One is the rho prime of T divided by 2, integral over omega of yt squared dx. Then I will have also the derivative of the integral of yt, which is here, is going to be rho t integral over omega of yt, ytt. And then in the last one, I will have the integral over omega of gradient y, gradient yt. Okay? So now if I integrate by parts here, as we did before for the wave equation, I pass the gradient from yt to y, I will get Laplacian, I will get a minus Laplacian, and these two terms here, right? These two terms here, because I will get what? I will get rho yt times yt and minus Laplacian times yt. This will be equal to minus, right? This will be equal to the minus the integral over omega of yt squared, right? But you see that then the combination of these two terms is 1, right? So yeah, 1 minus rho prime of t divided by 2 integral over omega of yt squared dx, right? With a minus here, and yeah, that's it. So what do I see here? I see that, you know, despite our intuition is that the impact of this term, right, on the energy of the system should be to damp energy down, because after all, the mechanical interpretation of this is that on my elastic medium, and I am applying a force, right, which is proportional to the velocity, but with an opposite sign, my intuition is the same as for rho, the density constant, and I will expect that simply the energy goes down. Why? Because at every time instant, I am applying a force which is, you know, opposite to the sign of the velocity. So somehow there is indeed, you know, more and more friction. There is, you know, the membrane will have more and more difficulties to vibrate, and this should produce a decay of the energy. Well, you see, this is not completely true, right? Why? Because you have here a term which is 1 minus rho prime divided by 2. So you see that actually, you know, the dissipative nature of the system is only guaranteed when the derivative of rho is less than 2, right? So if the derivative of rho is less than 2, then I can guarantee that rho prime over 2 is less than 1. Therefore, I am, you know, subtracting to 1 a number less than 1. I am keeping the positivity here, and therefore, right, the energy at least goes down, right? But if the derivative of rho, you allow rho to grow very fast, as soon as the derivative of rho goes too high, be above 2, I cannot even guarantee that the energy is being conserved. Okay? So we have therefore to be very careful about, you know, the behavior of the systems I am considering here when you allow for time oscillations. Is this good or bad? Well, it's bad in the sense that, of course, the analysis is more complicated, right? And therefore, we have to develop extra tools in order to understand what's really going on, right? When considering this kind of time oscillations. But it's very good from the perspective of the design of new devices like deep neural network in order to achieve different goals, right? Why? Because we discover that with respect to the classical dynamical systems, right, the fact of adding time-dependent coefficients introduces new effects, okay? By the way, So here I'm talking about the wave equation, but I could do the same for the harmonic oscillator, right? So I could do the same for the harmonic oscillator. And this brings us even closer from, you know, the behavior of neural networks, right? So you could consider, for instance, the harmonic oscillator, right? This is the one-dimensional ordinary differential equation copy of the wave equation. The wave equation is, if you want to, a system similar to this, right? Where the matrix A, right, rather than being simply a symmetric matrix and definite positive, has become an infinite dimensional operator like the Laplacian, right? But even, right, so this leads to, you know, the wave equation eventually. But the phenomena I am discussing here about the dependency effect on the behavior of damped harmonic oscillators, right, is actually true already, you know, at this very simple level. Because if I take this model, right, that I can rewrite from a mechanical perspective in this manner, and I know that this is a spring, you know, oscillating a spring that is being damped, so that whenever the spring is expanding in this direction, I am pushing on the opposite direction. And if I consider the energy, which is 1/2 x prime squared plus 1/2 the potential energy, the time derivative of the energy is equal to minus x prime of t squared. So it's fine, it's dissipative. But now if I consider a spring with a mass, now you could talk this, maybe you put here the mass is the same, right? We put the mass here. And I tell you, what are the dissipative properties of a spring with, you know, time varying mass? What is the difference with respect to the example, right? I could have taken here a constant mass and the computation would have been the same. I just add the mass to the energy and I see that there is a dissipative law, right? But now what is the impact of having a mass that depends on time? Well, apparently one will say, well, if the mass in between one M0 and another mass M1, like in homogenization problems where, you know, I have two elasticity coefficients, but okay, anyhow, they are between 1 and 2, the behavior should be some kind of average. So then if that is true, is it obvious that there is an energy for the system that decays? So what is, for instance, the behavior of the energy? M/T divided by 2 x prime t squared plus 1/2 x squared, which is really the energy, I will guess, the natural one for this system. I compute the time derivative of this, right? And I see exactly the same phenomena as for the damped wave equation. Why? Because now m depends on time, right? M depends on time. And then I have here, right, m prime of t divided by 2 x prime squared plus then m of t times x prime t x double equation. The equation m x double prime plus x multiplied by x prime, and therefore this is equal to minus x prime multiplied by x prime. So this is again minus 1 minus m prime of t divided by 2 x prime t squared, right? But you see the same phenomena as before, right? So the dissipativity, right? The dissipativity is only guaranteed when m of t is less than 2. Sorry, m prime of t is less than 2. So it means that, you know, when I am considering the mass on the spring that is very mild going up and then can go down very fast, and is mild going up, can go down very fast, if m prime of t is less than 2, then it's okay. I have at least I know that I have a dissipative system, right? And therefore, if it is dissipative, then I can expect by, you know, the Lyapunov arguments we have shown the other day, that it will converge, you know, to equilibrium. But, you know, what this computation is telling me, right, is that be careful if you allow, right, the density to grow too fast, right? So if m prime of t is greater than 2, then this is a warning. Be careful, because in principle, not even the energy seems to be dissipated. Okay, so when you look to this analysis, you can say, however, okay, why did we get this difficulty on analyzing the dissipativity of the system? Well, the reason is that when I computed the derivative of the energy, I got the term m prime. This is true. And once I got the term m prime, I have seen that I need to impose some upper bound on the derivative if I want to see really the dissipativity emerging. That's clear. But why did I get the term m prime on the derivative? Well, it's because I introduced the term mt on the energy. Okay. Was I obliged to introduce mt on the energy? Well, it was natural to do it, right? Why? Because the energy for an harmonic oscillator of mass m is simply m over 2x prime squared plus 1 over 2x squared, kinetic energy plus potential energy. And the kinetic energy is simply mass times velocity squared. It was natural. But was it compulsory? Not really. When I am in the context of the analysis of the long time behavior of ODEs or PDEs, as we have seen for the wave equation with damping, not always, you know, the analysis, the nature, the behavior of solutions emerges the most clearly out of the most natural energy. Sometimes modifying the energy helps, right? Then we could have said, well, what if I try a different energy? So maybe the energy I try, it should be some kind of energy in which I take some, you know, average mass, right? Why am I thinking on average mass? Well, I am inspired in homogenization theory, in composite materials. I know that, for instance, even if, you know, this m is time dependent, right? For instance, if fm were, you know, piecewise constant, maybe eventually there is some kind of averaging effect of the two constants, and this behaves, the system behaves like a kind of, you know, equation with some m bar. In principle, I am allowed to consider this energy. You agree with me that if, you know, whatever m is, m positive, of course, you are able to show that this energy goes to 0, then you are done, because both x goes to 0 and x prime goes to 0. So from a mathematical perspective, you are about building Lyapunov functionals. You are not obliged to use the natural Lyapunov function of the system. You can build your own, you know, Lyapunov functionals. And then if I compute the time derivative of this new energy, maybe this will guide me on how to, you know, choose m bar according to the ODE. Let us try to do it. Now, when I compute now the time derivative of the energy, I'm happy because now, because m bar is a constant that I still don't know which one it is, but it's a constant anyhow, there is no time derivative here. So this term will simply be m bar x double prime x prime. And the other one will be x prime, right? And now I say, do I have here something simple? Well, not completely, right? Because x times x prime is minus, right? X prime squared, that's nice. But, you know, the term m bar x double prime times x prime is something like, you know, this will provide the term x lead to a term which is minus nt, right? X double prime x prime, and then I will have also plus m bar x double prime x prime, right? So then if I do this, right, I get something more complicated. So you see, it's not so easy to guess a priori what the Lyapunov function should be when you are in such a complex scenario. Actually, for those that are interested on the interplay between neural networks and also the stability of finite dimensional dynamical systems and Lyapunov functions, there are some recent papers by Lars Grune, who is working in Bayreuth in Germany, right? And, you know, he has analyzed the use of neural networks to build Lyapunov functions. Okay. This is another interesting, maybe not so expected application of neural networks, is that, well, we know by Sivenko that a neural network can approximate any function. And for you could also say, well, if I'm looking for a Lyapunov function, why I don't search in the class of functions defined through neural networks? And in this way, for complicated nonlinear dynamical systems in which, you know, the search of the Lyapunov function can be something tricky, you know, these neural networks can help you doing it, right? So here the problem is slightly different because the difficulty came through the fact that I have here introduced, right, a second order system, right? So there is an interesting connection of this topic also with momentum ResNets. There is a recent literature on this, in particular by Gabriel Peyre and some other collaborators, and also some other independent works. You can find that in Google easily, right? So what is momentum ResNets? We say, what is a ResNet, right? So ResNet is the residual neural network that when I write the ODE version, right, leads to the following system, right? Right? Differential equations. So there is one reason. One is notationally is much simpler to write it down that way than, you know, to be forced to write it in, you know, with the, you know, the induction indexes. So one is the simplicity of the expression of ODEs. But then the second reason for this is that all the tools from the stability and the control theory of ordinary differential equations. Good. So then people said, well, if we have considered, you know, ODEs of this form, why don't we go to momentum, res nets, or momentum, neural ODEs? What this will be? Well, it's very simple. You just add, right, a second order term, right, on the equation under consideration, right? And then you can say, well, now, right, I can analyze the same problems again. And maybe if I am lucky, right, because the dynamics generated, sorry, x prime of t is now a vector, right? Of course, the theory of Cauchy-Lipschitz tells you that, you know, two solutions cannot get to the same point. But in this case, point means point times velocity, right? But if you just look for the location of the point in x, and you don't look to the velocity, then these 2 points can be sharing the same point in x, right? The same projection in x. So in particular, because of this, one could expect, right? One could expect that two different trajectories get to the same point, xt, at the final time, capital T, provided the velocity of each of them. So x1 prime t and x2 prime t are different, right? This is actually something we have seen on the dynamics of the billiard we were considering the other day, right? I said I take a domain omega, and then I can build a billiard in which maybe the red ball, you know, evolves in this direction, right? Something like this, and then 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 maybe eventually like this. Okay. And then I have another one, the green one, right? That starts here and moves in this direction, and then in this direction. Oh, you know, they cross at this point. So the two trajectories, right? They can collide at this point. This is actually what, you know, the game of the billiard. I mean, this is the basis of the game of the billiard, is the nonlinear dynamics, quite tricky, unexpected, very, you know, creative. You can generate playing with collisions, right? But you see, I said that this is a dynamical system. And now I say that there is a collision. It means that the two trajectories are getting to the same point? Not really, because as we said the other day, when I'm looking to the trajectories of the billiard, I have to consider 3 parameters in order to identify the position of one trajectory at a given time. The 3 parameters are 2 parameters for the position, x1, x2, and 1 parameter for the orientation, for the angle. So from a, say, phase space perspective, from the perspective of the ordinary differential equation, right? These 2 points are not located in the same, precise location in the phase space. They share the projection x1, x2, but it's very clear that while one is oriented in this direction, the other one is oriented in this direction. So from the perspective of the phase space, these 2 trajectories are positioned in different locations, right? Because I will need to, to make a full description. This will be x1, x2, and then there will be, the angle of propagation. And then, although the 2 points are sitting, they have the same projection x1, x2, the height corresponding to the orientation of the vector will be different, okay? The same happens here for residual momentum networks, right? The fact of adding this second order term in time gives you more freedom. Of course, the dynamics of the system is also more complicated. I have put here an epsilon that is not necessarily large or small. You could also make it large, but of course, when you make it large, you will be getting farther and farther away from the dynamics of the system, right? But when epsilon is small, right? When epsilon is small, then the dynamics of the system will not be very far from the dynamics of the neural ODE. In particular, it will be good for applications in data science in the sense that you will have the property of classification, but you further have the property, right, that while before, right, for classical, say, neural, if for neural ODEs, right, we could do something like this, right? And, determine who goes where, right? As I said, this is possible. But I said also, while this is possible, what is really impossible is that if you give me 3 initial points, then the map will be so that 2 of them will go to the same point and 1 will go there. This is impossible, right? Because here, right, I am violating, right? This violates the backward uniqueness of the neural ODE, right? But when I am now dealing with momentum, right, neural ODEs, right, things like this are now possible, right? But they are possible, as I said, right? So now it's possible. Now it is possible if we only determine the target, right, for X, but not for X prime, right? Because if you will determine if this will mean, if the interpretation of this will be that the full trajectory with the same X and the same X prime has to get to the same point, then this is not possible, right? But if you only tell me, that you have to arrive with X, but X prime is free, so one can arrive from the, vertically from the top and the other one from the bottom, up and down with different trajectories, then they can cross. But of course, this means that the 2 trajectories cross and they will continue being different, right? Precisely the same as in the mathematical billiard, right? The 2 trajectories cross, right? But they are different. One continues the green path, the other one continues the red path. Okay, so this is another, say, interesting observation now coming back to the topic of data science and machine learning, that you can learn out of the, you know, the theory of wave equations we are discussing here, right? Okay, so of course, when you are dealing with momentum res nets, right? So the limit process, right? Of course, when you are considering these kind of problems, right? So now in the context of momentum differential equations, if you are here and you pass to the limit when epsilon goes to 0, of course you will get the classical neural ordinary differential equation. There is no doubt. I mean, this limit process is perfectly true, right? So the more epsilon goes to 0, right? The more epsilon goes to 0, the less important this acceleration term is, and therefore you are converging down to the classical neural ordinary differential equations. But of course, the warning is, but when epsilon is very large, the behavior of, you know, the second order term of momentum ODEs and first order ODEs can be quite different. Why is that? Well, just check what is the behavior of epsilon x double prime plus x plus, you know, x prime, right? So this is the simplest case where all these terms is simply equal to x in the linear case, compared to the behavior of x plus x prime equals 0. So here, of course, the solution responds exponentially. This is just an exponential decay with exponential type equal to -1. While when you are doing the computation for, you know, for the second order equation, right? This is a second order polynomial. And then the roots are -1, lambda is equal to -1 plus minus a square root of 1 minus 4 epsilon divided by 2 epsilon, right? And then you see, as we have seen, this is the same computation as the overdamping. Now, the overdamping that was in the context of the wave equation or the harmonic oscillator manifested by a very large, you know, constant here, now rather is manifested on the dependency on epsilon, right? Because, well, what? So while epsilon is smaller than 1/4, you know, this is a real number. So then you have two eigenvalues that are not very far from -1, right? But as soon as 4 is very large, then this generates also an imaginary part and things start changing. Okay, so the spectral, you know, so here you see that the spectrum behaves differently depending on whether this number is negative or positive. Okay, so this is the typical situation we will encounter. So, of course, as usual, please be careful when you are dealing with this kind of maths. Nothing is completely obvious, but certainly, as I said, in the context of residual neural networks, it is legitimate to use all our understanding of wave-like problems to move from first order to second order when the epsilon parameter in the acceleration. So this is a, you know, this is a neural net with a mass. So it means like now the information is not traveling completely freely, but is carrying mass. So it produces, a dynamics where there is more inertia on it. Still, when epsilon goes to 0, you know that you are, generalizing these dynamics, and that you have extra features as those that the billiard allows, right? In which two particles can share the same position at the same time, provided they have different velocities, right? So this is what the rest nets do. And then you can achieve things that will not be achievable for, say, the classical rest nets, thanks to the fact that you are adding the momentum. And this mathematically corresponds to a rigorous, say, you can do it as an exercise. I mean, you apply Cauchy. I mean, this sigma is Lipschitz. So given WT, AT, and BT, this ODE, both the second order and the first order, have a unique solution. And then as a theorem, you can prove furthermore the solutions of this problem as epsilon goes to 0 converges uniformly on compact intervals to the solution of this problem, right? Of course, there is always some loss, right? Because, while here, the Cauchy problem has two initial data, of course, the last one will only recall the first initial data, right? So this is an information that you will lose, right? So there is some loss of information. This is why this is, what is called, this is a singular limit, right? Right? It's not a smooth limiting process. There is a change of type on the kind of differential equation, on the architecture of the neural network. There is a change of sign, of nature, right? This is why in the theory of perturbations of systems, this is called a singular perturbation or a singular limit or perturbation, right? And the output is that when you pass to the limit on the Cauchy problem, the velocity is completely lost. Okay, very good. But please keep in mind that our intuition, which is really conditioned by the proximity of this equation and this equation, stops when epsilon is still quite mild. In particular here, when epsilon is less than 1/4. When epsilon is large, our intuition fails. And then this has positive aspects and negative aspects, as before when we were talking about oscillations, right? It means that, the analysis is more complicated, but it also means that there is more room in order to generate dynamics that were not possible before, okay? Okay, so as I have said, is that, thinking on this momentum residual neural networks from the perspective of mechanics, I have said, well, this is like considering that the particle, that the neuron has some mass, right? Because, in the second order oscillator equation, the coefficient in front of the acceleration is precisely the mass. And I have said the mass introduces some inertia. So what is the link, right, with this inertia or memory effects and, the fact that we have moved from residual neural networks of order 1 in time to residual neural networks of order 2 in time? There is indeed the memory effects, right? So how can I analyze the memory effects? Let me do a very simple computation first. So let me consider the linear case again. And I say, oh, this is an harmonic oscillator with damping, right? So this is an harmonic oscillator with damping. The damping is of unit size because there is a 1 here, and mass equal to epsilon. This is the mass of the harmonic oscillator. Very good. Okay, and we know there is a dissipation law and everything. Now I can make a different writing of this, saying, well, but listen, if I group these two terms, and I write them like here. So I identify here what? I identify, maybe this, right? I identify here this derivative, right? Why? Because when I compute the derivative of this, I have two terms, right? Okay, so what is the link between this and this? Well, the link is that I could have written here, I divide the equation by epsilon, and I have something like this, right? And then I am multiplying the equation by this. So it means that this equation here becomes simply exponential t over epsilon x prime prime plus exponential t over epsilon x equals 0. Do you agree with this? It is correct, right? So if I will take here, you know, a derivative, this will be x double prime. I will get here 1 over epsilon x prime. I have 1 over epsilon x. And if I multiply everything by epsilon, I go back to this writing. Of course, the common factor exponential cancel out, and this equation is equivalent to this. Oh, but then I could integrate also this equation, right? And say that exponential t over epsilon xt plus then the integral from 0 to t of exponential s over epsilon xs ds, right, divided by epsilon is equal to simply the value of, sorry, there is a prime here, right? The value of this at, say, t equals 0, which will be x1, right? Very good. So now if you put all this together, what you see is something like this. Right? And if I will take, for instance, x1 equals 0, right? This will be simply x prime of t plus 1 over epsilon, the integral from 0 to t of exponential s xs ds. Okay? So recall that x1, right, are simply the initial data, x0 equal x0 and x prime of 0 equal x1. But in the context where you are using this kind of second order residual neural networks to classify data, typically you are given the data x0 and you can choose the initial velocity you like. But then normally you will place your data on a static manner on your, say, phase space. It's very natural to take x1 to be 0. Of course, you can put velocity on the initial data too, then things will get even more complicated, maybe also richer, but it will certainly be more difficult, right? But if I get into my room and I want to put order in my room, what I see is that the data are static, so x1 is equal to 0. What I can do is build a strategy for putting order on my belongings, which is more or less sophisticated and efficient. So, but it's very natural to, to make this x1 to be 0, right? This is at our disposal, and we can make it to be 0. So what is this? Then you realize that, what you realize is that out of this analysis, I have built a new class of ordinary differential equations, which are involving memory terms, right? And then this also shows that there is a link, right? There is a link between memory, neural, ODEs, and so momentum, neural ODEs, and neural ODEs with memory, right? Okay, why? Because if I, reproduce the same kind of arguments, you will immediately get to models of the form, right? The classical residual neural network I was considering right before, but where you are involving maybe instantaneous terms, but also some other terms involving the memory, right, during some time interval with some kernel, right, k t minus s. So maybe I should make it a bit shorter, otherwise we never fit. So I will take x prime of t, then plus wt, and this could be now a function that depends, right, both on the instant value of the solution, but then also through other coefficients that could also act as controls, right, on memory effects given by some kernel, right, depending on the solution, right? Maybe I should put it that way. Yeah, I could even add here another term, right? Some kind of, say, MS XS, that could be a control plus some kind of NS XS, NS. Okay, DS. Okay, so let me be a bit vague at this point. So memory effect. So what does it mean from the perspective of neural networks? Well, it means that, when you are transferring information, right? Before, we were transferring information from one layer to another layer, right? Like in Markov chains, right? What we are saying here now is that so maybe keeping, right, the memory to the effects, and then we are making a combination of, a few layers before we move forward. And this is, of course, very natural in the context of differential equations, right? First, because mechanically, this is like the same inertia effects on harmonic oscillators, first. Second, when you are doing numerical analysis, this is like moving from Euler-like one-step schemes to advance, to march in a time-discrete manner on the numerical resolution of the ODEs, right? But, it's also related, for instance, to gradient systems, right? So what did we say about steepest gradient descent? We say that steepest gradient descent was something like xk plus 1 equal to xk minus rho gradient j xk, but with delay, right? This was an exercise I left for you. You can also prove that the gradient descent with delay, right, converges, and that actually it might converge for a slightly larger rho, which means you can take, larger steps, right? And then you see that when you are doing this, you are doing something very similar to this in the sense that you are, adding memory. And now that you have written this kind of neural ODEs with memory, now you have a much larger class of neural networks to manipulate in order to, to tune it with your, say, given goal in mind, right? So from the point of view of elasticity, right? So this is linked, right, to viscoelasticity, right, which can be written, right, in the two alternate manners. It can be written as, equations involving also, other terms like, they don't appear in the context of elasticity, right? It's not even, right? So this is a wave equation with a damped. So this is a wave equation with viscous damping. right? Why the damping is viscous? Well, because before, for the wave equation, when we were adding damping, this was the velocity damping yt. But now this yt is multiplied by minus the Laplacian, so I am adding, right, the viscosity on the damping, right? Good. But this can also be rewritten for the same reasons before as a heat equation with a memory term, right? For instance, something like this, okay? So viscoelasticity or materials with memory, right? Lead to this kind of dynamical models, and precisely, you know, this kind of neural ODEs with memory term have been inspired on them. Of course, materials that are viscoelastic are, you know, used everywhere, in particular because they keep, you know, the property that of being elastic, but they have the very nice property also that they have memory effects. So whenever you press the material, you observe that the material is behaving in an elastic manner, but when you release the material, right, you observe that the recovery of the material is slower. It's not, you know, as say, you know, oscillatory as it is in pure elasticity, right? And, you know, this is why, you know, viscoelastic materials are those we use typically when we are designing furniture for our office, for our home, you know, the sofa or the bed, right? So these are materials that are elastic in the sense that when we are sitting or lying on them, you know, they can absorb our weight. But these are also materials that when we, you know, we turn around, they don't react in a purely elastic manner, something that will be quite, you know, uncomfortable, but they react with memory in a smoother manner before they recover the original position. Okay, good. Okay, so we have seen how these principles in mechanics, the links between various models, and in particular, the possible presence of inertial terms and memory terms can help us designing, you know, richer families of neural networks enjoying better properties, in particular in the context of classification. So let me now go back to the boundary control of the wave equation. Which is certainly one of the most prototypical problems on the control of partial differential equations, right? In which, given a membrane on which we are looking to either vibrations or acoustic propagation, right? We now try to look to the control problem on which, you know, y, depending on x and t, is the solution or state. This could represent either elastic vibrations or acoustic waves, right? So the geometry of the domain omega, right, can be arbitrary. This could be either in 2D or in even higher space dimensions. But what really differs in this model with respect to the classical wave equation is the fact that U, right, is the control, right? So U is the control, right? So the question is then, you know, what are, you know, the question is, what are the new dynamics we can generate, right, by a suitable choice of the boundary control, right? And in particular, you know, can we, for instance, find a control U depending on X and T, right? Localized on the boundary d omega cross 0t, so that, for instance, the solution at time capital T reaches the equilibrium. So we start from a configuration in which if nothing is done, if U were equal to 0, the solution will be vibrating all the time, right? This will generate energy preserving oscillations of this membrane omega, right? Now the game to play is whether the action of a suitable control here U, right? U can, you know, reduce the dynamics, drives the dynamics to the zero equilibrium of absorbing all the energy of the system. So we have, for instance, considered the case of transparent boundary conditions in the one-dimensional wave equation in which, or the perfectly matching layers, in which this was realized through a feedback, but with a feedback law, we expected at most to get some exponential decay, right? So then here, right, we are trying to really drive the solution to equilibrium, right? So reach equilibrium in finite time. By means of an open loop control. Right? So in this controllability problem, we are not assuming that U has to be given. We are not restricting the controls to be given by a feedback law. We are allowing U to be totally free. So it means we are in the context of open loop control. And this is why we can expect achieving equilibrium in finite time. And the first remark to be done is that there is a new phenomenon is that for wave problems, for wave equations, the velocity of propagation is finite, and therefore such a control property will require that capital T, the time horizon, right, is large enough. And you recall, this is something didn't happen for the finite dimensional systems. So this is new with respect to A, B, finite dimensional systems, because in that context, when the system is controllable, the control target can be achieved in any time possible. Okay, very good. So is this relevant for when you are in the context of, for instance, residual neural networks? It is relevant when we are considering residual neural networks. Well, when we are considering residual neural networks, we are in a finite dimensional context, right? Typically, on which, you know, even though it's nonlinear, the problem is nonlinear, you can think in the same terms as for, say, ordinary differential equations, at least for small perturbations, and expect that the control properties are independent of time, so they might be also independent, right? Time for a residual neural network is equivalent to the number of layers you need. But what this theory here is telling me, be careful, right? Because there is a phenomena we know from the theory of partial differential equations. This is why it's so interesting to make the link between continuum mechanics and data science, right? And in particular, you know, when analyzing the behavior of deep neural networks, because in the context of continuum mechanics, the models are partial differential equations. And for partial differential equations, there are new phenomena emerging, like in the context of the wave equation, the so-called finite velocity of propagation. So this somehow is a warning. Be careful, because maybe if the number, you know, the width of this neural network gets larger and larger and larger, your residual neural network will start behaving more like an infinite dimensional dynamical system rather than a finite dimensional dynamical system, because the dimension is growing and growing and growing. And in some sense, then you could expect that the same phenomena as we observe for wave equation could emerge. This will mean that maybe, right, when you are in very high dimension, the classification, say, capabilities of the residual neural network might depend also on the number of layers you have, right? Because layer, as I said, is equivalent to time in the context of continuum systems, okay? So that's also an important warning, right? When you increase the dimension, you are closer to PDs, then warning, finite velocity of propagation can emerge, and this might mean that to achieve your goals, for instance, supervised learning or classification, the number of layers might need to be large, okay? So why in the context of the wave equation, so things can be, you know, analyzed more carefully, but you see already that when you are dealing with the one-dimensional string, right, even if you apply here a control U0, right, y equal u0 at x equals 0, and you apply here a control u equal x, y equal ul at x equal l, you need the time of control to be large enough in order to achieve the zero target. Why? Because in particular, you know, if you use simply the representation of the solution of the wave equation using the D'Alembert formula, you see that the solution here, yxt, only depends on the initial data, y0 and y1, and is independent of the controls u0t and ult. ULT. Of course, here the controls, right, depend on time, right? And this means in particular that at time, for instance, capital T over here, right, the solution here is fully determined by the initial data, is completely insensible to the presence of the control, is completely insensible to the presence of the control UL and U0, and therefore the solution will not vanish if time is short enough. A different interpretation in the multidimensional case is that, yeah, fine, you are controlling the system all along the boundary, right? You are controlling the system all along the boundary. You can do whatever you wish on the boundary. You are totally free. This is an open loop control, so you can manipulate waves, right? But you should keep in mind that waves on the wave equation propagate along rays. So, you know, before this wave departing from here gets to the boundary, right, there is nothing you will be able to do, right? So then, you know, the time of control, right, the time of control will be at least the time needed for all rays of geometric optics to reach the boundary. Right? And this also suggests some other interesting geometric configurations where, like, for instance, you are considering a domain omega, right? With, for instance, two perforations, right? So I make two holes here, one and then another. So I take a perforated membrane. So this is a perforated membrane. And I tell you, well, listen, I have controls, but the controls are only acting on the exterior boundary, right? I don't have access to these perforations, right? So I cannot really act on the boundary of these two holes. So this will be a typical situation where, you know, waves, right? Waves will not be controllable when the action of the control is limited to the exterior boundary. Why do you think that is the case? Why do you think that in such a, well, after all, simple geometric configuration in which, you know, the membrane has been perforated, as we do often on, you know, on the design of optimal structures, we try to make it lighter. So you try to keep, right, the same structural properties, but making it lighter. So you try to remove unnecessary material out of it. Why do you think that in such a geometric configuration, the membrane will not be controllable out of the exterior boundary? What is the effect of having these two obstacles or these two perforations built in the domain, built in the medium? Do you see any difference with respect to the free propagation of rays that we observe in a membrane in which, you know, the boundary has just one connected component? Do you see any particular ray that maybe has a behavior that is not the one could have expected in this other membrane where the domain is full rather than having these two perforations here, here, and here? Yeah, there is a trap ray, right? So you have a ray. Thank you, Anna. You have a ray that is trapped. So in this case, whenever the domain has some perforation, right, there could be a trapped ray, right? That will, this is like a billiard ball that is, ping-ponging, right? Endless, trapped in this, say, in between these two obstacles. This ray will never get here to the exterior boundary, and this will make, right, the system not to be controllable. So this means also be careful when you are designing, neural networks, right? Because if for some reason you generate some kind of, effects here, right? Maybe, I should, right, draw it that way, right? Okay, so this will be like a manifestation of the fact that in some of the, components of the neural network, you have introduced heterogeneities, right? That could mimic the behavior of these two obstacles. Then maybe something, strange could happen here in between these two layers, making that, your neural network doesn't really behave as it would, right, in the completely homogeneous case, right? Again, as I have always said, this can be good or bad, right? So this is bad in the sense that it makes the analysis more complex. So the more heterogeneity you put on the network, right, the more complicated the analysis will be. The positive aspect of that is that whenever you use heterogeneities, contrast between the behavior of one neuron and the other, you can also generate new phenomena that could be of a specific interest, like, for instance, succeed on, on trapping, in some sub-network part of the dynamics of the system. And this is what we are saying here, right? So in some sense, the dynamics is ongoing on the whole domain omega, right? In our neural network, the dynamics could be ongoing along the whole width of the neural network. But when you put heterogeneities, that in the case of the neural network will be manifested on, on the intensity of coefficients on the different, say, dimensions, right? This could generate some localized effects that you could not anticipate out of the homogeneous dynamics on the whole membrane or network, okay? So as I said, this has these two sides, right? Okay, very interesting. So now, anyhow, the key point I wanted to make here is, right, is that, the velocity of propagation is something that, we don't see on finite dimensional systems, right? And this was also one of the reasons to realize, I mentioned the other day how the Kalman rank condition cannot be generalized easily to infinite dimensional system, in particular because, saying that the rank is equal to infinity is not so meaningful, right? The rank could be infinity, and yet you control all the even components of the system, but you miss also an infinite dimensional projection, right? So I indicated this first difficulty on the extension of phonetics is the science of communication and control and communication. And we have understood in the context of the linear finite dimensional systems AB that a possible use of that idea is to, rather than considering the control system in which you have to figure out the tricky impact of a control on the behavior of the system, it is much easier to look to the adjoint problem of observability, in which the system is free of control, and it is just about, discussing how much of the energy of the system I can recover through the observer associated to the control operator B, meaning B star. Okay? So what is the dual observability property? So the dual observability property consists on considering the adjoint system, which in this case is just the wave operator again, without control, so zero boundary conditions, and of course, the data, right, given at the terminal time, right? So this is a bit surprising. Why the adjoint system, right? Why the adjoint system for the wave equation is the wave equation itself, right? I said the wave equation is ytt minus Laplacian y, right? And now when I write the adjoint wave equation, I write the same system again. Why is that? Why the adjoint system for the wave equation is the wave equation itself? You have any guess? Well, what was the definition of the adjoint, right? So the definition of the adjoint, right? When we look to, you know, the adjoint, what do? We say, I take this system, sorry. And I move to the adjoint. Okay, yes. But, you know, moving to the adjoint was due to the fact that, you know, when I multiply one of the components, so for instance, x prime plus ax by 5, or vice versa, the equation for phi by x, by integration by parts, one term should become the other. Now, what happens when you do integration by parts here, right? Where, for instance, you multiply this adjoint equation by the original state equation y. Well, I have two time derivatives, so I have to integrate by parts twice. When I integrate by parts once, I get a minus sign. I mean, integration by parts with respect to time. When you have a minus sign, sorry, you integrate by part once, you get a minus sign. But when you integrate by parts a second time with respect to t, you have minus, minus, plus. So of course, right? So when you integrate by parts, precisely because we are integrating by parts, the second time derivative remains the second time derivative, but with the corresponding sign, which is, you know, plus. And the same for the Laplacian. The Laplacian with Dirichlet boundary condition is a self-adjoint operator. Right, by Green's or Stokes formula, when you integrate by parts once on Laplacian, you get a minus sign, but when you integrate once again in order to transfer the whole Laplacian, which is second order in x, into the adjoint variable or the state variable out of the adjoint variable, when you transfer the Laplacian from one component to the other in both senses, you see that the sign is preserved. This is why the adjoint for the wave equation is the wave equation itself. And we say, oh, but this is great, right? Because then the energy of the system, which is the integral over omega of the gradient of phi xt, the potential energy, plus 1/2 of the kinetic energy, this is conserved, right? The energy is equal to the energy at time t, which is precisely the one you input on the system through the initial data you plug in on the adjoint, right? And this is important, right? Because we have seen, for instance, that when we are doing, you know, the gradient descent algorithm for the, you know, computation of the control or the numerical approximations of the control, this is always an iteration in which I first solve the adjoint system, and then I plug in the solution of the adjoint system to solve the control state equation. And with the residual, I have to adjust the data for the adjoint. But here, my goal is to drive the system to equilibrium, right? So the residual will precisely be the gap between the actual solution y and the target 0, 0 in that case. So the residual will show up at the time capital T. This is why it's so important that in the application of control theory, I place the data for the adjoint and time capital T, because this data on an iterative loop in order to find the optimal control will precisely be the residual. Okay? So in order to, you know, achieve a successful control application, the data have to be in the final time. Now, if you ask me, is there any difference, right, on the solvability of this adjoint system, depending on whether the initial data are on capital T or are on 0? The answer is no. The answer is no. It's exactly the same. Why? Because if I reverse the sense of time, you know, solving this problem in the backward sense is just a consequence of the fact that it can be solved also in the forward sense. So from the perspective of existence and uniqueness, there is no any problem. You could have taken here the data for phi to be at t equals 0. But from the perspective of the, you know, of the adequate coupling between state and adjoint, is very important that one moves forward with initial data on the state and the other one moves backward with data at time capital T. Okay, very good. So now, what is the observability problem then? What is the observability problem? You see, our goal is to control waves from the boundary. Our goal is to control waves from the boundary. But then on the observability problem, the question will be the same. Can you observe waves from the boundary? So what does it mean for the adjoint system? For the adjoint system, right, the observability inequality then will be can I recover the energy at the time capital T out of the energy concentrated over the boundary? How do I measure the energy concentrated over the boundary? Well, you see, over the boundary, phi is equal to 0, right? So if I will look to the energy here, right, I will see, well, phi is equal to 0 on the lateral boundary, right? So if I take, this is omega, this is time, right? So phi is equal to 0 here on the boundary. And because phi is equal to 0 on the boundary, of course, the time derivative of phi is equal to 0. And the tangent derivative of phi is also equal to 0. I mean, the function is phi is 0 on all these lateral boundary of the cylinder. So whenever I take time derivatives and tangent derivatives with respect to the curvature of the boundary of the domain, both derivatives are equal to 0. So out of the total energy of the system, what is simply left is the normal derivative, right? So then the observability inequality reads normal derivative d sigma, which is the boundary measure with respect and dt less than that. And this for all solution of the adjoint system. Okay. Of course, as is classical in PDEs, our convention is that if this is the domain omega, mu, which is the outer, right, vector, normal vector, right, is the outer unit normal vector. So mu x is the outer unit normal vector, right? And then the normal derivative of phi is equal to the gradient of phi times m, right? So it's the variation of phi on the normal direction. And indeed, it's, you know, physically meaningful, right, to consider the normal derivative. Why? Because when you are, you know, taking, for instance, the vibrations of a string, and, you know, the string is fixed on the boundary, there is a vibration inside. Indeed, I expect that, you know, the derivative on the boundary, in some sense, you know, is a measure of the amplitude of the energy of the vibration inside, right? And the same in the multidimensional case, right? Where when I take a vibration inside, right? A vibration inside, I expect that the slope here on the boundary is giving me a measure of the energy inside. Okay? So this is the kind of you know, discussions that was presented in the Siam review paper by Louis Lyons in '88, and that opened a new perspective to these problems. Because then people said, well, listen, the control problem here is hard to handle. You know, you are asking me to somehow produce controls that will be able to annihilate the vibrations of the system. So this control U, excuse me, this control U is playing the role of an anti-wave, right? Waves propagate inside the domain. While they are propagating inside the domain, they move completely freely. You know, they vibrate, they keep their energy, they keep their orientation. And then when they get to the boundary, because my goal is to drive the solution to zero, I have to kill, to annihilate all these waves. Somehow the control is playing the role of an active anti-wave. But you see, this is not easy to construct for several reasons, right? First, and the most, is that, you know, the geometry of rays, of propagating rays, can be complicated. So then I should anticipate which ray is coming to which point at what time, and how much energy this ray is carrying out of the initial datum to design what the control should be. This is something that is very complicated to do at the level of the, you know, control. The open loop control is not easy to design, precisely due to the intrinsic complexity of the wave propagation process. But this one, people said, this should be much easier to handle, right? Why? Because I'm just looking to, right? I'm just looking to the classical wave equation, and then you are asking me whether a given inequality is fulfilled by all solutions of the wave equation. So then the problem simply becomes, right? The problem simply becomes, problem is given a domain omega in RD, bounded, right? We take the domain bounded. In practical applications, domains are always bounded, right? Find a time, capital T, such that, right, the energy of the solutions, right, is bounded such that there exists a constant C, which of course will depend on time, right, such that the energy of the three vibrations, right, is bounded by the energy concentrated on the boundary, right? And then note that phi being a solution of the adjoint system, right, it represents a free vibration without control. Okay, very good. Excellent. So now question, can we prove this kind of inequalities, right? So this is not something, again, that is very simple. I mean, you could think on the similar terms, right? You could think on similar terms in terms of propagation of rays, but then you should develop, you know, tools that are proper to micro-local analysis, in the sense that you should be able to really follow how much energy is propagating along each ray, then check whether when it gets to the boundary, you are able to recover the full energy, and then somehow pile up, right, the observation along each trajectory of the billiard to build such a global inequality. This certainly is the most adequate when you are looking to very, very sharp results. But here we are not really interested on, you know, getting the most, say, sophisticated result on that setting, but rather, you know, giving a proof in which we could get an intuition of why this is in fact true and can be proved rather easily, right? So then what I'm doing now is I'm giving you the proof that this inequality is true, right? And this uses multiplier techniques for partial differential equations that appear in different contexts. In particular, if anyone here is, you know, is an expert on semilinear elliptic equations, you probably know the Pokojaev identity, which allows to, for instance, show that some nonlinear elliptic equations don't even have any non-trivial solution, right? Okay, so this is a generic tool in the context of partial differential equations with different possible applications. One of them is the proof of this inequality. But before I do the proof of the inequality, I would like to argue why this inequality is the one we need. And the proof is very simple. It's the same argument we did on, so why, let me show you why the observability inequality suffices. And the argument is very similar to the one we employ. It's actually the same, right? But just put in the PD context for finite dimensional system. You see, we have this wave equation with a control that we don't know, right? And this is our goal, right? To find this control. We have initial data that are given. And we have a target, right? The target is yt equal to ytt equal to 0, right? And then we also have the adjoint system. And we have the adjoint system. Okay. Now I multiply the state equation by phi. I integrate by parts in omega cross 0t. What do I get? Well, actually, when I multiply here, of course, by phi, and I integrate to the right, I get 0. To the left, What do I get? So I get 0 equal to what comes out, the product of the wave operator applied to phi and y, integrating by parts. But when I integrate by parts, the wave operator on y goes onto the wave operator of phi. So everything vanishes also on the inside. So the only terms I get are those corresponding to the, integration by parts on the boundary. So what I get is simply the integral over omega of y t phi minus the integral of y phi t, the difference from 0 to t that comes out of the time integration. And then I also get, the boundary terms coming from the integration by parts in a space, so the Green's or the Stokes formula. So this will give what? This will give me, right, the integral over the boundary of what? Of the normal derivative of y times phi. Oh, but phi is equal to 0 plus, because there is a change of sign, y, which is the control u, times the normal derivative of phi. So I get this, right? But if I really want the target to be 0, in order to achieve the target, y has to be 0 at the final time. This is the representation of the fact that that the state equation has reached equilibrium. Then, of course, the term at time capital T will go away. So then this means immediately, right? This means that, the control U successfully controls the system to ytt equal to 0, 0, right? If and only if the following equation holds. The equation then is simply that the integral, I write first the last term because this will play the role of the quadratic term on the, right, u d phi d nu, d sigma dt, and then I will have minus, right, yt at 0, which is y1, right? The integral of y1 times phi at 0 plus the integral over omega of y0, right, times y0 times phi t at 0, which is phi t at 0. And this has to be equal to 0. So you see that this is completely equivalent to guaranteeing that the control U is such that yxt is equal to ytxt is equal to 0. And once I see this, I say, well, but this again has the same structure as I identify on the characterization of the control for finite dimensional systems, thanks to the duality with the adjoint. So then I see that, this means that, to find the control, it suffices to minimize the functional, right, J, which of course depends on the data of the adjoint at time capital T, which is the integral over the boundary, half of the integral over the boundary, the normal derivative of phi, d sigma dt, minus the term in here, minus the integral over omega of y1 phi 0 minus phi 0 minus phi 0 phi t0 dx. Okay? Where do I minimize? Well, I have to minimize in the space this makes sense, right? So this is over the Hilbert space H, which is H10 omega, the Sobolev space H10 omega, right? Which is the energy space, right? And then if I really are able to minimize this functional so that I find a distinguished minimizer, right? If this is the minimizer of J, then the control U is just the normal derivative of phi over the boundary. So what I realize is then that although, I mean, the notation is different because we are in the context of partial differential equations and so on, everything is similar to the finite dimensional control theory. So the control problem disappears. I just look to the adjoint problem that I can nicely understand, right? And the only thing I have to do is to minimize such functional, right? I will argue now why the minimum exists. But once you know the minimum exists, or even if you don't know that the minimum exists, which is often done in practical applications, the problems are complicated enough so that you don't really know whether maybe the minimizer exists, right? You will just run a gradient descent iteration. And the gradient descent iteration in this context will be the same as for finite dimensional systems. You do a discrete induction in which you first solve the adjoint equation, you plug the control given by the adjoint equation, you solve the state equation, you test the residual, and out of the residual, you correct the data for the adjoint equation to do one further step, and then evaluate again and again and again, the gradient in order to descend. Right? So it's the same principle. And now you say, can I minimize this functional really? Can I minimize? I look to the functional, I say, this is linear, this is quadratic, so the functional is convex. The functional is also continuous. We are in a Hilbert space. So what really matters in order to, the continuity of the functional needs to be discussed also, but this is easier. It will actually arise when we are discussing also the observability inequality. What really is more tricky is, as usual, the coercivity of J. So you say, okay, all is fine, but is J coercive? It's not so clear, right? Because you see, if I was arguing in classical terms, I will bound this integral over omega by Cauchy-Schwarz, and the norm of phi 0 and phi t will appear in omega. It will appear the energy of the solutions, while the quadratic term that is pushing the functional J up is only given on the boundary. So in order to do this, right, is J coercive? And the answer is if and only if the observability inequality holds. And the observability inequality is the one I have written here, right? Is precisely this observability inequality. So you see that now, thanks to this classical duality principle that Wiener already anticipated and that was formulated sorry, by Jean-Louis Lyons in this paper in Science Review, the whole problem is reduced to proving this observability inequality. Okay, so now let me show you how you do it. We still have, let me try to do it, proof of the observability inequality. So we have this adjoint wave equation. right? Phi on the boundary is equal to 0. Phi t is equal to phi 0t. Phi t0 is phi 1t, right, with omega. Right? The goal is to prove that the energy is less than a constant, right, times the normal derivative. Okay, and the proof will be done using multipliers. And energy estimates. Okay. Is there any questions so far? Otherwise, I will move to the proof. I will move to the proof. Okay, so what is multipliers? We have already seen the main ingredients when dealing with the damping of the wave equation, right? Why that? Because we have seen that in order to show the effective decay of down wave equations, we needed to perturb the energy. And then all my arguments was, multiply the equation by yt, multiply the equation by y. But then our interpretation later was in terms of the Kalman-Rank condition. We said, listen, when you are doing this without saying, you are using precisely the Kalman norm in which, the Euclidean norm is replaced by B star, B star A star, B star A star squared, and so on. And these terms, B star, A star, and so on, were precisely those that were telling you which multipliers one should use. So even though it's hidden, we have already seen at the context of the PDEs that even simpler issues like just the decay rate of PDEs needs of using these cross effects through multipliers. And this is what we do here. So here what we do is multiply the equation by x gradient phi, right? So then what do we have? We have, 0 is equal to the integral from 0 to capital T, integral over omega of phi tt minus Laplacian phi, and I multiply by x gradient phi. So what is x gradient phi? Well, x is just the vector, x1, xd, right? Which belongs to omega. It's just the coordinate representation of the material point of the wave medium, right? The gradient of phi, of course, is the classical gradient. So it's the derivative in x1 up to the derivative in xd. And therefore, the scalar product of x phi is a first order partial differential operator in which you see the sum for j from 1 to d of xj d phi dxj, right? Okay, good. So then out of this identity, I get immediately that the double integral of phi tt x dot gradient phi, the two quantities here are a scalar, right? So phi is a scalar function, so phi tt is a scalar. Phi is a scalar function. This is a vector, but x is also a vector, and the scalar product is an scalar, right? This minus, this integral is equal to 0. So the only thing we need in order to see what comes out is to expand a little bit these two terms using integration by parts. By the way, Professor Kai was asking recently whether there was some literature on Maxwell system. Yes, there is. So I can show you later but I mean, it's precisely the same kind of computations you will do if rather than considering the scalar wave equation, you will be considering more complicated wave problems like the Maxwell equation, the system of elasticity, or the Schrodinger equations in particular. Even KdV, Korteweg-Debré linearized equations, they all can be treated by very similar techniques, okay? Okay, so then let me analyze the two terms one by one. So the first one will be, what do I do with the double integral of phi tt x gradient phi dx dt? So what I do is the following. I integrate once by parts in time, right? So one of these time derivatives, I put it into the gradient of phi, right? And I will get this. And then I will get this remainder term, right, that comes out of the integration by parts at the initial and the final time. Now, because this is phi t, because this is phi t times the gradient of phi t, I can always write it as the gradient of phi t squared divided by 2. So then I can write this term as the integral of now what? It will be x over 2 multiplied by the gradient of phi t squared, dx dt. And this is the gradient of all this squared, right? And then these terms remain the same. And now I do again integration by parts, right? Then I have the divergence of the vector field x, but what is the divergence of the vector field x? It's just the dimension d, because I get x1, the derivative of x1 with respect to x1, which is 1, plus the derivative of x2 with respect to x2, which is 1. So I have d dimensions, I will get d. Of course, I have another change of sign, so this becomes a plus now. And I have here d over 2, the integral over omega of phi t squared dx dt, plus the same term. So you see, this is nice. This is nice because I identify here, right? I identify here the kinetic energy. So this first argument was successful, right? So I decided to multiply the equation by this multiplier, which is in principle kind of involved. Of course, x gradient x phi can also be written as the modulus of x times the radial derivative of r, because the vector x is always pointing in the radial direction. So I have decided to, to use this multiplier. This was not totally clear why, but it turns out that at least in the first term, it was successful in the sense that I made, the kinetic energy emerge. You will tell me, yes, I mean, you made the kinetic energy emerge. I mean, you got it also when you were doing the conservation of energy, but we don't see, Enrique, we don't see at all where, the normal derivative that you need here is coming out. Okay, but it's very likely that this normal derivative will rather emerge out of the, the integration of the second term, because it's an integration by parts in space, right? So then I go, to the second term that had a minus, recall. And then when I have is, the gradient of phi, I apply Stokes or Green's formula for integration by parts. Of course, the minus becomes a plus. And then the Laplacian, one of the gradients of the Laplacian goes to the other side, right? X gradient phi dx dt, and then I have the integral over the boundary, right? Of now what? The normal derivative of y, of phi, times x gradient phi d sigma dt, okay? And now I ask you, what is x gradient phi? You know, we know that phi on the boundary is equal to 0. Then, you know, when we decompose the gradient of phi into the tangential component plus, you know, the normal component, we see that the tangential component vanishes. So this is simply, the gradient of phi is simply, you know, the normal, which is a vector, right, times the normal derivative of phi. So when I come here back, right, what I see is the first term that I don't manipulate by now. Minus the term on the boundary where now, you know, this vector gradient phi is parallel to mu multiplied by the normal derivative of phi, which is a scalar. Therefore, what I get here is the scalar product of the vector x with mu, and then the normal derivative squared, right? So then what I get here is the scalar product of x mu. I don't use the vector notation, but I just make it, I make emphasis on it through this scalar product, and then the normal derivative of phi. Okay, very good. Now I expand this system again. So let me use the notation of summation of repeated indices, right? So this will be the sum on j, right? This will be the sum on j of dj phi times dj of all this. I just use the notation of repeated indices so that I don't need to write the sum here, okay? And then this will be, you know, the dj of what? Again, using the notation of repeated indices here, I could write this as being xk dk of phi dx dt, and this term similar. Now, when I expand this sum, then I will have two terms. One will be the jth derivative of xk. Well, what is the jth derivative of xk? Is the delta Kronecker, right? Because when k and j are equal, this is 1. And when j and k are different, of course, the derivative of xk with respect to xj is going to be 0. So this is the delta Kronecker, right? And then I get the term, right, dj k of phi, a second derivative. And the other term remains the same. So now I say, oh, but this, if this is the delta Kronecker, I get here the gradient of phi squared, right? And here I get dj phi sk d squared gk phi dx dt plus the boundary term. Okay? So do you have any question until now? Okay, good. So note that here we are also, right, using the summation of repeated indexes. So actually, when you compress the notation a little bit, then what we have here is, right, is the integral over omega of x gradient. And then here I have the gradient of phi squared divided by 2. It's the same principle as before, right? Why? Because you see, whenever you take the gradient of gradient phi squared divided by 2, the 2 goes away, and then I get the second order derivatives that I have here. And the fact that, you know, I am writing xk gradient in k of dj squared, it means that I am really doing this, right? So maybe you need to be, to do it yourself, convince yourself maybe in two-space variable, write down this formula. If you are used to this kind of compact integration by parts using, vector values, vector fields, and so on, it's easier. Otherwise, you can check yourself. And then I say, oh, but then because I have this here, right, I should integrate by parts again. I should pass the gradient to x. This will give me the divergence of x, and I will get something nice, again, related to the potential energy that I show here emerging. But when I do integration by parts here, I will get again d, right, with a minus sign and with a 2. So then what you get here is 1 minus d over 2. The integral right? This term here goes away, but I get the boundary term, right? The boundary term is normal derivative of x nu, normal derivative of phi. Why the normal derivative of phi? Well, because as we said, the gradient of the boundary was tangential derivative 0, because phi is 0, and normal derivative. So all the gradient on the boundary is the normal derivative of phi. Of course, you cannot do this reduction on the domain omega. It will not even make sense, right? What is in the interior, the boundary derivative? No. But over the boundary, when you restrict this gradient to the boundary, because phi vanishes and therefore the tangential derivative vanishes, you just get the normal derivative, right? Okay, so then when you put these two identities together, what do we get? Oh, by the way, now we are so happy, right? Because this is the potential energy. And this is the observed boundary energy, right? So we didn't complete the proof of the observability inequality that we wanted, but we were so lucky that using this multiplier, integrating by parts on the first term, we got the kinetic energy, and integrating by parts on the second term, I got the potential energy plus, the observed energy on the boundary. And these are the three ingredients, kinetic energy, potential energy, and observed energy on the boundary that I need to cook the observability inequality. So there is some hope, right? So now let us put together what we did. So if I add the identity coming from the second integration by parts here, and the identity coming from the first integration by parts, what did we get? We got that 0 is equal to out of the first term, the kinetic energy with factor 1 over 2, right? So I go here, sorry, it's d over 2, not 1 over 2, d over 2. D over 2, good. Then I got, also with a plus sign, 1 minus d over 2, right here, of the potential energy. Right? Good. What else do we have? We have also plus, listen, is this, let me see. I think I missed something here, right? Let me see. Yeah, so we did this. Oh, there was this term, and this term here had a minus sign. And then there was a minus sign here. So there was a minus sign here. And then when I added the 1/2, then what remains here is the 1/2, right? So sorry, because here there was also the term coming from the previous boundary term, right? There was the integral over the boundary of x nu d phi dn squared. So this term appears twice, in the first integration by parts in x and in the second integration by parts in x. but we are lucky that they don't cancel. I mean, sometimes we like that they cancel, right? The identity becomes simpler, but here we want it to remain because this is the, you know, the boundary observed energy that we need to use in order to establish the observability inequality. So there was a -1 plus 1/2. Sorry, then this is a -1/2. This is a -1/2, right? The integral over the boundary of x mu normal derivative of phi squared dx dt. But there was something else, right? Because out of the, yeah, so this was the term that I forgot here, right? So this is the danger of not fully writing down the identities. Oh, but there is also this term, and this term is what? Is simply the crossing, right, of the integral from 0 to t, sorry, of the integral over omega of phi t x gradient phi dx from 0 to t, right? And then because I want to estimate the energy out of the normal derivative of the boundary, the way I like to write it down, so to conclude, you know, the lecture today, and then tomorrow we can just finish the proof in 2 minutes, but I let you think on it in case you want to, is the following. I have d over 2, the integral, I mean, this is the contribution of the kinetic energy, plus 1 minus d over 2, the contribution of the potential energy, plus a term that I will write in red because it really, I don't like it. I mean, it looks like a reminder term, right? Coming from here, which is equal to 1 over 2, the integral from 0 to t, integral over the boundary of x mu, normal derivative of phi squared, d sigma dt. So now let me tell you what are the terms I'm not totally satisfied of. There are two aspects that are not completely satisfactory on this identity. There is some that are great, right? So here I see kinetic energy, I see potential energy on one side that I have to estimate out of the normal derivative of the boundary. That is great. We are, you know, in the right path. But there are a few things that I don't like. So here I have d over 2, and here I have 1 minus d over 2. And this is not a mistake. You can remake the proof. You see that these are the real numbers. You could say, well, it doesn't really happen. I mean, when you did the dissipativity of the energy by Lyapunov function, you have also different weights on the, you know, on the kinetic and potential energy. Yes, but this is much worse because in dimension, say 1, this is fine. This gives you 1 over 2, and this gives you 1 over 2. So in dimension 1, we will be very close to the end of the proof. But in dimension d equal 2, this term goes away, so you lose the potential energy. And in dimension d greater than 2, and in particular, I mean, these results are totally true independent of the dimension d, right? In dimension d greater than 2, this term is even negative. So this is a danger, right? And the last one is that there is this reminder term that in principle, I don't identify with my problem. My problem was about estimating the energy out of the energy on the boundary. And this term seems to be bothering me, okay?